Hi guys, it's Sunday. I'm recording for Monday's lecture. Just want to check in to see how you guys are doing also. Are you feeling stressed or things at home weird with, the shutdown or whatever? If you have anything you want to talk about, not chemistry related, feel free to email me and we can keep in touch that way, or we could do a Zoom chat too if you just need an adult person out of your home to talk to. Just want to throw that out there. In any case, we're going to start today on page 15 in your packet. So please turn to 15 in your packet and let's get started. Okay, so this is called a potential energy diagram. It basically is just showing you how energy is moving in a reaction. Okay, so I'm going to just give you guys a reaction. So I'm going to say this is the reaction Y plus Z yields YZ plus heat. Now, because heat is on the right-hand side of the reaction, I know that this is an exothermic graph. Okay? All right, so the y-axis is potential energy, usually in joules, or it could be in kilojoules. The bottom is reaction progress or reaction coordinate, or you could just say time. Okay, so at point A, the arrow, so this is 0. Let's label this 30 joules. So at letter A, this arrow representing the potential energy of your reactants. So remember that your reactants would come before the arrow. So this is Y plus Z. And this is how much energy they have to start. So like potential energy in their bonds or whatever. We want the reaction to move forward. In order to do that, they have to get over this hump. This area of heat or energy, let's label that 40, is called the potential energy of forward activation. So it's your forward activation energy. Oh my gosh, that's so funny. I'm recording something for school.
But then can I play that thing that we
Maybe, yeah, maybe. Okay, so forward activation energy.
So you're talking to yourself?
Yeah, I am talking to myself, exactly. So you start at 30. In order to get to the top of the hill, you need to get to 40 kilojoules or joules. I'm going to label it kilojoules because I think that's more likely. So how many kilojoules of energy do we need to get up to the top of the hill? 10. So it's like you're going up a roller coaster. So in order for the reaction to occur, you need to go up the hill, and then the reaction will start moving and you'll go down the hill. So letter C is potential energy of the activated complex. I'm not going to write potential energy anymore because that's the unit here. So this is your activated complex. Your activated complex is where it's like a transition state. So bonds begin to break or form. It's the transition. Okay. So I'm at the top of the hill, and so since that is, the arrow goes all the way down to 0, and it goes all the way up to 40, that means it took 40 kilojoules of heat to get to the activated complex. All right, and then as I move down the hill, I finally make it to the end where I have YZ. So letter D, the end line to the bottom, represents potential energy of your product. Okay, so there's a few more lines we need to talk about. Let's talk about letter E first. Okay, so letter E is if we're starting on the right-hand side, we're doing the reverse reaction and trying to get to the end. So letter E represents reverse activation energy. Sorry, that looks like an N, energy. Okay, so that's the energy to start the reverse reaction. And then we have letter F, and this one's really important. So this one is in the center. So this is the arrow that does not touch the top, does not touch the bottom. This represents delta H, which is also called enthalpy, and is also called heat of reaction. Those three things mean the same thing. The formula for delta H is this. So delta H is equal to heat of your products, so energy of your products, minus heat of your reactants. So I'm just going to look at products. I'm going to go here, and why don't we label that as 10 kilojoules. Okay, so 10 minus the heat of my reactants, 30, and I get negative 20 kilojoules. Okay, which should make sense because the negative means heat is being released. So like you're losing some heat, and that is what the graph is showing you too. You start high, you lose heat, and you get lower in energy. So the negative means exo as well. Okay, I think that's it. So negative delta H, exothermic. Okay, so let's flip to page 15. It is the same kind of thing. Oh, I forgot something, never mind. Flip back to page 15. Okay, so the last thing we're gonna say is what happens when a catalyst is added. So when you add a catalyst, so a catalyst speeds up a reaction. So a catalyst works by lowering this hill. Yeah, I am talking to myself, thanks. So this is with a catalyst. Hey Maddox, don't mess with that, please. A catalyst lowers forward. And Maddox is spinning in circles right now. And reverse activation energies. So basically, it just lowers the energy needed to start either the forward or the reverse reaction. Okay. All right, now let's move on to page 16. Okay. Moving down. Okay, so what you guys should notice right away is that this graph looks like it's the opposite, and it's the opposite because this is an endothermic graph. So this time the reaction would be like YZ plus heat yields Y plus Z. So since heat is before the arrow, it's entering, this is an endothermic graph. Okay, so let's just go through and label this as well, and this will be a lot faster. So we have YZ here because letter A, 0 to the first line represents your reactants, potential energy of your reactants. Letter B, the energy to get me to the top of the hill is my forward activation energy. So the energy to start the reaction. Let's label that 40. All right, so if I start at 10 and I need to get to 40 kilojoules, I need to put in 30 kilojoules of energy to get the reaction going. All right, so now I'm at the top here. This is where my bonds start to break. This is called your activated complex. And then after the bonds completely break and I get Y and Z, letter E represents your products. So the one that represents the products is always your final line all the way down to 0. So let's mark that. What should we call that? Let's say that's 30 again. Okay, so 2 more lines. We have letter F. So letter F is if we go the reverse reaction. So if we want to start here and go backwards. So this is potential energy of the reverse activation. This is reverse activation energy, the energy needed to start the reverse reaction. And then we have letter D here, which is your delta H, heat of reaction, or enthalpy. Okay, so just as a reminder, delta H is equal to heat of product or energy of your product minus energy of your reactant or heat of reactant. So it's always the difference between your products and the difference between your reactants. Okay, so let's go over and calculate that out. So I'm looking over here, my products are 30, my reactants are 10, so I get a positive 20 kilojoules. That means I put in 20 kilojoules of heat. So a positive delta H is endothermic. All right, and then the last thing, let's do green again, is what happens when a catalyst is added. So same thing, a catalyst lowers the hill with a catalyst to speed up the reaction. Okay, so what I would like you guys to do now is just, let's just do page 17, and then we'll review this again on Tuesday, because this tends to, I don't know, it tends to be tricky. So Tuesday we'll wrap up the unit on potential energy diagrams, and then the last keyword, which is entropy. We'll take it slow since this is the last week before spring break. Woohoo! All right, so pause your video right now and try to do the questions on page 17. And when you get back, I will be back to go over the answers. Okay, so in the first set of questions, the vocabulary. So it's the energy needed to start a forward reaction. So this one is forward. What are you guys doing in there? Okay, let me push pause for a minute. Okay, recording again. So that is the energy needed to start the forward reaction. So it's forward activation energy. The type of reaction for the graph which increases in energy means it looks like this. Okay, so if we start here with our energy and we go up, we're adding energy, so plus energy. And when we add energy, that is an endothermic reaction. The energy at the end of a reaction, this part right here, this is your potential energy of products. You're fine. Okay, the energy a reaction begins with, potential energy of reactants. Okay, the sign of enthalpy present in an endothermic reaction. So endothermic reaction, you're adding heat, so the delta H is positive. The energy needed to start is an activation energy. Since it's asking for reverse reaction, it's the reverse activation. E sub A is the symbol for activation energy. The big E is energy. Stop doing that. Lower, and then A is energy of activation. I can still see you if you're going in a different room. Don't mess with the glue, buddy. All right, the type of reaction in which a graph decreases in energy. I can show you how to do it. So you start with energy here, and you decrease. That means you're getting rid of energy. So this is an exothermic reaction. All right, next one. The sign of enthalpy in an exothermic reaction, negative. If you forget that, it's on the bottom of table I. And then the total heat gained or lost in reaction is the definition for enthalpy. Or the other words are heat of reaction or delta H. Okay, and then the last question, number 10, is an exothermic or endothermic reaction favored by nature, and why? So an exothermic reaction is favored by nature because it lowers the energy. See, right here, that's what's happening. Energy is getting lowered, and when you have lower energy, you're more stable. Okay, so let's just stop there, and then tomorrow we'll do the multiple choice and finish the packet with entropy is on the last page. Yeah, I think we'll probably end up finishing it unless we just do this. I'll decide tomorrow. Anyhow, I hope you have a good day. You will have a Google Classroom homework assignment, so check there. See you later.